So the question is should I hold office hours Monday night or not? I can tell you this, if you make me come in Monday nights, my mom is going to be pissed. She wants to take me on my birthday.
Is it your birthday on Monday?
No, it's Saturday, but she doesn't get me for my birthday. My girlfriend gets me for my birthday.
Oh, shit.
Who's planning on being on campus Monday night? Oh, you got
Wow.
me kidding me. Yeah. We decided not to have Physics X because no one was going to be here Monday night.
Well, we said we would come if you did it, but we probably wouldn't come if you didn't.
No, that's not the way it went down.
I don't know about everybody else.
You what?
I had my hands up when you were asking whether it was
Monday night, Monday night. Okay, well, I'll tell you what, I will assess it's going to depend on how far I get today as to how long your assignment's going to be, because we got to get through certain material, and I'm going to add a couple questions, so.
Please test.
Depending on how long it is, the other option is to shift your quiz to Thursday. I'll see where we get and make a judgment. But raise your hand if you would come, if you felt like you needed help, raise your hand if you would be around on Monday night to attend office hours. Okay. It would have been easier if no one raised their hand. It's okay. All right, any outstanding questions from last time before we get started with today? Because we're going to just keep going with what we did last time. Keep banging on it. Okay, all right. So we talked last time about the fact that ultimately we're going to make some statements about symmetry, and invariance and special relativity is largely going to be a statement to that effect. But in order to make the statements sort of in a sophisticated way, we've got to develop some mathematical tools to describe, for starters, transformations, and then we start piecing on what we need in order to talk about invariance. So the last time we talked about groups, obviously, as sort of the mathematical structure, sort of the minimal mathematical structure that we require when we talk about a set of transformations. And there's many different examples of sets of transformations. We talked about the defining axioms for groups, some examples of what is and is not a group. And then the more important thing we talked about were representations of groups. And I might go ahead and say this because I might not be precise in my verbiage today, but I sometimes am a little loosey-goosey with the word representation. Technically, we have, for example, a group element, like we might represent it by a matrix, and then we think of that group element as acting on something like a column vector. The representation is technically this thing. It's because you're representing the transformation in the group. But to represent it, you kind of have to have this idea of it acting on something. And I will sometimes refer to this as sort of defining the representation, because once you know what this is, you know the form that this has to take. So I will sometimes refer to these things as the representation, but technically this thing is always the thing that's being represented. This is the transformation. So if you get confused, just ask me and I'll clarify. Okay, but we know that from last time we have these sets of transformations, but then we have to think carefully about what are they acting on, because they might look different depending on what they're acting on. And we talked about rotations and looked at, but depending on the shape you're rotating, the form of the rotation might be different. We talked about degenerate representations, things like that. And so now, what else? Yeah. Okay, so now what we want to do is we want to talk about invariance a little bit. And to get to invariance, we actually have to introduce yet another piece of sophistication, which is interesting because at the end of this, you're going to figure out that we're talking about something that you've known all along, and it's just that no one's ever called it that. Okay? So there's a teaser to get you all excited. You all seem very excited. That's good. It worked. Okay. So before I get going, a lot of what I'm going to write is going to look very ugly, and it's largely because we're thinking of things in terms of matrices. So remember, we can draw pictures, but we can't make equations out of pictures. We need something sort of with numbers and so forth. So we're going to work with linear representations and use matrices. I'm not actually going to write out matrices. I'm just going to draw symbols and say that thing's a matrix. But a lot of what I'm going to write is sort of heavy-handed because we're using matrices. Later, we're going to find a more elegant shorthand notation to get rid of thinking about matrices. That's something called index notation that I know you're all very excited about. But for today, we're going to be sticking with matrices. So here we go. We want to form an invariant. We know we have we can represent transformations, for example, by matrices. And so the idea is roughly the following. If I have some object, say I'll represent it by a column vector, and I know how it transforms under some element of a group, maybe I multiply it by a matrix, then if I said you want to find invariants, the first thing you might think is, oh, you like want to find like scalars. Like things where the group always acts like the identity. It doesn't change the thing. That's what we mean when we say invariant. And so that might lead you to think that the only thing you can ever work with are scalars. Okay? So for example, if you're thinking of rotations as your symmetry transformations or your transformations, then you might say, I can only ever work with scalars. Well, that's not very interesting. What we find more interesting is to take things like vectors and make scalars out of them. Okay? So the idea in broad strokes is if we can find something that transforms one way and then find something that transforms in the opposite way, if we combine those, the transform of this might cancel the transform of this. Right? You buy that?
Yeah.
Let's write it down. Okay. So here we go. If I have let me see. We are going to take a cue from what you are all familiar with in terms of taking things that transform and building invariants out of them, and that's going to be the dot product. So we all know the dot product gives us an invariant, a number, a scalar, and the notation that we might employ in terms of matrices for that is we take a row vector and we use the rules of matrix multiplication to combine it with a column vector, and then we have a rule for what that gives us. I'm not even going to write it down because I know you know how to do that. And so this is a way of taking two things which are complicated and combining them into something which is invariant. Okay? And this is going to be sort of the motivation for what I'm about to do, but the way I'm about to do it is more formal. Okay? So here we go. Let's do this over here. For a matrix representation R, and again, this is where I'm being loosey-goosey because this is actually the thing I'm going to act on with the matrix, but I'm going to call the representation by that thing. For a matrix representation R, we can form the dual representation R twiddle as follows. Okay, so I've got some set of things that I know how they transform with the matrix, and that's what I'm calling R. And now I'm going to introduce a new set of things called R twiddle, and these R twiddles are defined as follows. If A is some transformation on the group, so this is maybe like a rotation matrix if you're working with rotation, so A is just one of the transformations, then the way that R transforms is that R goes to A acting on R. So A is a matrix, R is maybe a column vector, and that's what we talked about last time. Okay? Then the transformation for R twiddle is going to be weird, and this is because we're doing this with matrices. It's going to transform as A inverse transpose R twiddle. Okay? Now lots of stuff there. So the twiddle it's just a label at this point. It's just so that you know it's not just an R. Okay, so nothing too meaningful there. The inverse, this is a matrix. You know that you can invert a matrix. Transformations we're working with are invertible, so you can always take the matrix inverse. And then transpose, you all should remember from linear algebra, you just switch the rows and columns of the matrix. So that's a funny looking thing, not well motivated yet, but this is what we get from it. Then, the combination R twiddle transpose R is invariant.
What the heck is going on?
Which?
Is that like upstairs?
Yeah.
Yeah, that's weird. Okay, so I argue that starting with this, if we can cook up something like this, then this is invariant. Okay, so let's prove that that's the case. So we just take this thing, and what I'm about to do, we're going to do all semester. So if any of the notation or things I'm about to say are confusing, let me know. So I'm going to basically take this, and I'm going to do to each of these this thing here, okay? So R twiddle is going to become that. So let me put a big bracket. And then that whole thing is transposed because I'm transposing R twiddle. And then R does that. Okay? Everybody good? All right, and now we do what I affectionately call the transpose dance. If I have the product of two things and I'm taking the transpose, how do I break that up into the transpose of the individual objects? You reverse the order, exactly. So this transpose is this transpose times this. So this becomes R twiddle transpose, A inverse transpose transpose AR. And you can already see the magic that is emerging. The transpose of the transpose is nothing. And so this is R twiddle transpose A inverse A, and it's almost like it was meant to be. Okay? We get right back what we started with. Everybody on board? Good. Okay, so I forgot our cards. Where's Alex? Is Alex here? Oh, there you are, sorry. If I call your name, you have to let me know, because I sometimes can't pick, I see your face on the picture, but I can't pick your face out of there. So Alex, I have, it's weird saying Alex, because I'm Alex. I'm talking to myself. So I can answer this question in principle, because all I've done is given the first name. What do you think these are going to look like? Like I've told you how they're going to how they need to transform. What do you think they're going to look like?
Well, if it's a matrix, it should be a vector.
If what is a matrix?
Your A.
If my A is a matrix, then we wrote this as a column vector. So what do you think this is going to look like?
Row vector.
A row vector. Okay. Do you think it's going to look just like this, but a row vector?
Not necessarily.
Okay, that's actually exactly the answer. Looking here, if we look at this example that you're all familiar with, you might think, okay, so let's go back to this because you're all comfortable with this. Which of these is the R twiddle?
No.
It's this one. This is the thing we would be calling R twiddle because you notice it's transposed compared to this. And then this is what we're calling R. So you might think that R twiddle is really just the same thing as R, you just transpose it. Okay? And you would, based on this one example, you would be justified in thinking that. Okay? That's unfortunately not going to be the general case. Okay? So what we have to do is we have to ask, how do we get R twiddle? Okay? And for R twiddle, it turns out that there is a definition that if you start with an element of R, you can obtain an element of R twiddle by applying something which is called a metric. Now the metric, the notion of metric is going to play a central role in this course. In fact, I would argue that we're going to write down more metrics than anything else. Okay? Right now, it's sort of being introduced in this very weird abstract place. It's how you go from a representation to a dual representation so that you can form an invariant. All right? But this is really sort of the more abstract fundamental definition, and it's important because the notion of metric goes way, way beyond just like general relativity or even special relativity. Like the metrics are things which you encounter in many, many contexts. We talk about them in particle physics. And they are generally the way that you connect a representation to a dual representation where the idea is to take something from here and something from here and make an invariant out of it. Okay, so the same kind of story pops up if you're trying to work with spinors. So what I want to do is ask, all right, what does the invariance of this tell us about the metric? So combining this combination being invariant with this definition, what, if anything, does this tell us about the metric? Okay, so let's actually just do this. So we have R twiddle T R. Now I can use the metric to relate R twiddle to R. So this is going to be GR twiddle, or sorry, GR transpose R, because R twiddle is GR. It's a joke. That's not general relativity. Okay, hey, you know what? You all took dance lessons 5 minutes ago. What do? We do that, thank you. We do the transpose dance. You should have seen it when Jacob Wachowski was in this class. That boy, he did the transpose
What
dance.
was the dance? Can you reenact it for us?
I don't want to. Anyway. Okay. Sorry, detranspose. Okay. And then we have this nice result that the one thing about a metric is that it's always symmetric. So G transpose equals G. So if you ever find yourself writing down an expression for a metric, if you're not writing something that's symmetric, you're doing something wrong. Okay? So I can replace this with R transpose GR. Okay? Now the claim is that this is invariant under any element of the group G. Therefore this should be invariant under any element of the group G, because they're the same thing. So let's see what the invariance looks like when we work in terms of this expression. So RTGR, if I replace R with AR, because that's how R transforms, and then I replace R here with AR, because that's how it transforms, then, man, we did a lot of mileage out of this. We do the transpose dance, R transpose A transpose G, A, R. And for this to be invariant, what do we want this expression to give us in the end? Yeah, the thing we started with. Okay, that's what it means to be invariant. You start with something, you do some stuff, you end up with the same thing. So we literally want this to be equal to R transpose GR. Well, staring at that, what can you extract out of it?
That the A, T, and A somehow equal 1.
Yeah, A transpose GA equals G. Everybody see that? This is going to form the sort of starting point of what we're going to do next, and it's going to actually take us to our concrete examples. So, to put words to the flow of math that I just threw at you, we started all of this by saying we have these things and we know how they transform. We're going to introduce these hypothetical things solely to be able to say this combination is invariant. From that, we can figure out how these things have to transform. But then, I haven't told you how you actually create these things. And so I'm giving you a rule that says if you start with this, you can create these R-twiddles by using this metric G, but that story is only consistent if G satisfies this. For any transformation that you're talking about. Okay? We good? So let's get out of this formal crap and do some examples. Ready? Here we go. Okay. So excited. Chance is my next spectrum. Okay. There are two ways that we can use this. Two ways to play. All right, there's two things we can do with this. I could give you the group G. That is, I could give you the set of all these A's. So I could tell you what all the A's are that I'm talking about. And then from that, you can find what the metric is. Because it has to satisfy this equation. Okay. Chance. What's the other thing that you think we could do with this?
We could use G to figure out anything that's in, or little g, the metric to figure out anything that's in big G.
Good. We could give you little g, and then you can use that and that equation to find the g, or the set of transformations. Okay? I'm going to do both for you. I'm going to do this as an example, just to see where all this connects to stuff you're familiar with. And then we're going to use this to uncover special relativity. Okay? So let's start with the thing that, I'm going to do two different things. I'm going to start with the transformations and then find G, but we can obviously reverse the process because it's all related through that one expression. So here we go. And now that I've thoughtfully erased everything that I wrote, are there any questions before we Oh, good. All right, awesome. So, blazing through this. I'm now on the first page of today's notes. Such progress. So, what we're going to do is we're going to start with an example with which you should be somewhat familiar, which is just rotations in 3 dimensions. Okay? I'm not going to throw anything weird, abstract at you. This is stomping ground that you've seen before. Now, when I refer to rotations, I am going to refer to what are called passive rotations. And you can think of passive rotations as rotations of the coordinates, where you leave objects fixed. Okay, so just to lightning on that, if you set a coordinate system up and you, for example, draw a vector, you could either rotate the coordinates and leave the vector fixed, that's called passive, or you could keep the coordinates fixed and rotate the vector, that's called active. There's obviously like this one-to-one mapping between those two, but in this class, we are always going to be transforming coordinates. So we're always going to be interested in passive things. So we're going to do passive rotations. When you write down rotation matrices, if you're not familiar with it, there's a minus that goes in different places whether you're doing an active or a passive rotation. You could draw that picture again and say rotate by positive 30 degrees, and you get a different picture if you do the vector versus the coordinates. So you could figure that out on your own. I trust you can figure that out. Okay, so we're going to do passive rotations of coordinates in 3 dimensions. And so our group G is a, let's see, it's a compact because you rotate by an angle, but all angles you rotate by are limited. 0 to 2 pi, and then depending on how you set up your rotations, some of them only go from 0 to pi. It's compact. It is continuous, because angles are continuous parameters, so there's technically an infinite number of rotations you can do. And it is non-abelian, because rotations don't necessarily commute with each other. So some of the words that we were introduced last time, this is the ones that apply to this case. Now, what I'm going to do is I'm going to not write down every single rotation, because we would never leave. There's an infinity of them. But I'm going to kind of break them down into 3 independent categories. It's certainly not the only way that you could do it. Many different ways to do it. But, just to make it simple, we'll talk about a rotation around X, a rotation around Y, a rotation around Z. And then you can build an arbitrary rotation in terms of combinations of these. I can rotate by a different angle for each one of them. Okay, so I'll give them different angle labels, where it's important to remember that these are all continuous parameters. That's why this is an infinite group. Okay, so what I want to do is sort of explore a little bit of the mathematical structure of this, and in particular how this bears on invariance, because remember, this whole story right here, that's awesome.
Yeah, you did it twice.
Yeah.
I thought it might have been on purpose.
I'm consistent. No, I probably wrote it. No, I wasn't even looking at my notes when I wrote that. Anyway, okay. All right. I lost my train of thought. Oh, physics. Yes, we're doing physics. Sorry. Okay, so this story we developed by motivating and thinking about building invariants out of things that transform. So if we're going to talk about rotations in 3D, we should start ourselves out with some invariant. So of the things that you encounter out there, when you talk about rotations in 3D, and I want you to give me something really concrete and physical, what is something that is invariant under rotations in 3D?
Spheres.
Yes, but the problem is that a sphere is super degenerate in its representation, because the sphere itself is a scalar under rotations if you're rotating about the center of the sphere. Every rotation you do is basically like the identity. So I'm thinking of something that's associated with things that do transform, but is a scalar. It starts with an L and rhymes with the length of a vector. Any takers?
The length of a hectare.
Yeah, the length of a hectare. So I don't quite know what a hectare is, but it's like some unit of length, or is it area? Is it area? Yeah. Anyway, okay. No, so the length of a vector, this is important. The length of a vector is invariant under rotations, right? I can spin you around and you're still as tall as you are. But the vector itself transforms. That's what's important. You want the invariant to be built out of something that does something interesting. Okay, so here's what we're going to do. I'm going to think about 2 points in space. Oh, that was stupid. It's even stupider. Okay, 2 points in space, A and B, and they're each going to be coordinatized by 3 coordinate positions. And then I'm going to talk about, as a sort of prototype vector, the distance between them, which I'm going to call delta S. And so you all know how to calculate this. You take the difference in the x positions and you square it. You take the difference in the y positions and you square it. You take the difference in the z positions. God. And you square it. Okay. It's just that 3-dimensional form of the Pythagorean theorem. Doesn't matter which way you do the subtraction because you're squaring it anyway. And then the shorthand we're going to use for this going forward is delta x squared plus delta y squared plus delta z squared. Okay. So that is the length of the distance between these two. And then you might say, well, what vector are you talking about? Well, we could talk about the displacement vector moving from this point to this point, the vector that begins here and ends there. Okay? So what we're going to do is we're going to write this thing in a manner that kind of is going to let us tease out this structure. So I'm not going to think so much about delta S, but rather delta S squared. And so we'll do it like this. Okay. And I think you'll all agree that if you do the matrix multiplication of this, then you're going to get exactly this squared. Good? Okay, so now I've got this thing that's invariant, but I can do a coordinate transformation. I can do a rotation in 3 dimensions. And so we can ask, well, how do these things transform if we do a rotation? So I'm going to give them new names. And these are going to be primes. So in the new coordinate system, this point is going to become labeled by these 3 things, and this point is going to become labeled by these 3 things. Remember, the points I'm talking about are not changing. It's the coordinates I'm using to describe them that are changing. These are passive rotations. Okay? And here's the important thing. In this, I am going to assume that the vector, those are the components of the vector which point from this point to this point. Okay. The vector is a linear representation of the rotations. That means that this thing is going to be, well, let me write it this way. This is actually the way I tend to write it. Where R is some rotation matrix. Okay? So the question then is, okay, what about this? You know, what is the rule for transforming this? Well, we can actually infer that because we see in this case that this guy is literally just a transpose of that guy. And so what I can do is I can untranspose it for a minute, make it a column vector, then use the normal rotation rule, and then transpose that back. Okay? Okay, so let's do this. So I've kind of got where the R matrix, the thing that's actually going to do the transformation, how it's going to appear in this representation. And then I've actually kind of seen how it's going to appear for this dual thing. Now I want to come back to this statement and say that the length squared of this vector has to be the same in the old and the new coordinates. So I can evaluate this in the old coordinates, or I can evaluate it in the new coordinates. It doesn't matter. I have to get the same thing. Okay? But what I'm going to do is regret erasing that. What I'm going to do is I'm going to write this using this rule and write this using this rule. Okay? So again, I can, if I want to get this back to a row vector, I can do the transpose dance on those things, and then this thing, which is just this term, is going to become the transpose of this times the transpose of this. So the transpose of the column vector is just that, and then I've got R transpose. And then this thing right here, I'm going to replace with that expression. Okay? So, I want this thing to be equal to this thing. Therefore, what can, rhyme short, pardon, there you are. What can you tell me has to be true in order for this to be equal to this? For this to be equal to this.
R transpose R is the identity.
Bam! Never going to ask you guys hard questions. Well, I'll ask Gage hard questions. We'll do that in senior design. Okay. All right, you ready? Here we go. I started with the transformations, a quantity that I kind of know should be invariant into those transformations, and I kind of wrote down this sort of representation of how I'm going to affect those. I gave my conditions for the invariant, and I end up with this condition. Compare that to this. The top result is the more general story. In this particular example, we have R transpose R equals I. So Colton is going to tell me what G is.
The identity.
Yes. In this example, G is the identity matrix. Literally, if I say G is the identity, you probably would have left it out of here and just written A transpose A, and then you would have probably written the other side as 1. It has to be a matrix because these are matrices. So there's a lot of like implied matrices. I might write 1, but it needs to be a matrix if it's being equal to other matrices. So if that's ever confusing, raise your hand and say, is that a number or matrix? And I'll be happy to clarify. But what we've done is we started with a set of transformations, and by looking explicitly at how they work, comparing with this condition, we have found the metric that underlies this system. And it's an incredibly trivial metric. It is so trivial that despite the fact that you have been doing this since calculus -11D, no one ever said to use the metric. When you learn the dot product, okay, your calculus teacher probably said, oh, the dot product of two vectors is achieved by taking one of the vectors and applying the metric of Euclidean space to turn it into the dual vector and then contracting the dual vector with the original vector. Do you remember that?
Yeah.
No, because they wouldn't have said it because the metric you would be using is the number 1. It's the identity. Okay? But we need this because we're going to study situations where the metric is not the identity. So you have to really dig into things you're comfortable with. Places where there was supposed to be a 1 and they just left it out because everybody knows this one, there's a 1 there. Because we're going to tweak 1 and make it different things. Okay? Any questions about that? Now, I introduced the metric as this just sort of a formal way to go from the representation we start with to the dual in order to be able to combine this with this to make an invariant, excuse me. But many of you have heard the word metric before. God knows it's come up in politics enough. You tend to think of a metric as something associated with distance, right? Like it tells you how far apart things are. Well, that's actually exactly what is happening here. Because if you think about it, the way that you should have written this, but you never did, was like this. You should have, in order to say something about length, taken coordinate differentials, which in and of themselves don't have any notion of distance. They're just like labels, and this is the label XA, this is the label XB. And the actual thing that says this is what the distance is this piece right here, okay? To make that concrete, let's consider a slightly less trivial case. Let's think about what all of this would look like in polar coordinates. If I take 2 points in polar coordinates that are separated by a delta r and a delta theta, what is the answer supposed to be for what this distance should be if I'm working in polar coordinates?
Delta r squared plus
Yes, yes.
delta r squared plus delta theta delta r minus squared.
Yes, yes. I'll write it slightly differently, but yes. So it should be delta r squared plus r squared delta theta squared. Everybody remember that? Okay. So what's the metric?
0, 0, 0, R.
Too many zeros. Too many zeros.
R 0. Oh, yeah.
Everybody good? If you matrix that out, then you'll get this. Okay? If you didn't think about the metric, you might have just written delta r squared plus delta theta squared. Okay? So the metric is the thing that's really telling you how to correctly combine these coordinate differentials to get a meaningful length. Yes?
Will the metric like always be symmetric?
Yes. The metric will always be symmetric. Now, in a geometric context, that actually gets to a really deep thing, which is a question of whether the space we're dealing with has this quantity called torsion. And in this class and in classical GR, you usually have a torsion-free condition, which we will impose. You can relax that, and you need to when you talk about spinors, or when you want to try and write down a gauge form of gravity. But what people tend to do is they tend to take the antisymmetric part of the metric and separate it out into what's called the torsion tensor. So, but for what we're going to be doing, the metric is always going to be symmetric. Okay. So, questions? Lots and lots of formal stuff, but hopefully connecting to something that you were working with early on. Okay, so now we are in a position to say something about special relativity. And as promised, this is going to be a situation where I'm going to follow through in my example of approach 2. I'm going to just give you the metric, and then from the metric, we will figure out what the transformations are. You can just yell it out, especially if
Okay.
someone raise it for now.
If we're given the metric as, the trivial solution, which is the identity matrix, aren't there multiple situations that applies to? So how can we find the group?
Yeah, no, that's a good, so I guess what I should say, yeah, so that's actually an excellent point. It's not a complete specification of the problem just to hand you a metric. What I have to do is I have to give you a metric and a coordinate system. And then what you're doing is you're uncovering the transformations of those coordinates that are consistent with that metric. But I have to tell you, I mean, really and truthfully, like the coordinate labels are not important. Like, I could give you the metric of polar coordinates and then call my two coordinates x and y. And you might not like it, but you're working with polar coordinates. They just have weird names because x is playing the role of r and y is playing the role of theta. But generally speaking, you have to specify the coordinates and the metric. An additional part of this story, which we're talking about geometry, which is largely local. But you also, when you provide coordinates, have to tell me their ranges because that determines some topological things. So if I give you an x and I say it goes from minus infinity to infinity, that's an infinite thing. But if I say x goes from 0 to L, then you're talking about a topological thing. X might be a circle, x might be a line segment, something like that. Okay. All right. Let's see. And the other thing I should stress is the coordinates or the things that you're transforming, and this might be something that's not reflected in the metric. Because the tools I'm giving you, by the way, like we just talked about distance, and I'm going to talk about relativity, and we're going to talk about distance. But the tools I'm giving you apply to very abstract cases. Like we use these tools to apply to spinors in particle physics, which have no correlation with like distances in space-time. So one of the other things that you sometimes have to specify is whether the elements of the thing you're transforming are real or complex. Okay, because that's not always obvious from the metric if you write it down. Okay. All right. Okay, so special relativity. It can be stated as the following. Physical laws should not change Now, we've already written down sort of a way of saying relativity, but it was in words, and we talked about symmetries, and now I'm going to make that more concise. That's the point of all this. Should not change under transformations. A little caveat, continuously connected to the identity, and we'll talk a bit more about that later. For now, you can just ignore it, which preserve space-time intervals of the form delta S squared equals minus C squared delta T squared. Man, I'm just getting lazy. Delta T squared plus delta X squared plus delta Y squared plus delta Z squared. Okay, where the transformations that I'm considering are always going to be from one Cartesian coordinate system to another. Okay, it turns out that if you want to transform from Cartesian coordinates to, for example, spherical polar coordinates, you can do that in special relativity. It's just another coordinate system. But the mathematics of that changes the form of the equations and gets you halfway to general relativity because of the stuff you have to do. So the statement here is we're going to be transforming between rectilinear coordinates. And what I want to do now is write down the metric. And we can actually figure out what the metric is, because if we look at that expression, if we just write down a set of coordinate differentials, then Ryan, what's the metric?
-1, then identity after.
Yes, exactly. -1, 1, 1, 1. Okay. Okay, first point of contention. In this class, I prefer to use this metric convention where the minus sign is on the first and the rest are positive. There are many contexts which reverse that. They make this one positive and they make these negative. The only thing that's important is that the time and the spatial components have a different sign. It's really not that important which one has the negative sign. Of course, it changes a lot of expressions depending on where that negative sign is. I can tell you why I think this is gooder, because there is a point in the physics when you go far enough where you have to take the determinant of the metric and since I often work in 2 dimensions, 4 dimensions, 6 dimensions, 10 dimensions, 11 dimensions, sometimes 12, and often 26. If you use this kind of metric, the sign of this never changes. If you put your negatives on the spatial parts, then the determinant sign flips back and forth as you go from even to odd dimension. So for me, it's just this has always got the same sign no matter what dimension I'm working in. So I'm partial to this convention just because of that. Otherwise, there's really no difference. Nothing is easier or harder. Okay? So this thing we're going to call eta. A general metric I will refer to as G. For special relativity, we give that a special name. We call it eta. And this is the Minkowski space metric. in rectilinear coordinates or rectangular coordinates. It's so fancy. Okay. You could take this space and you could apply spherical polar coordinates, and if you do that, the metric will change. You'll get the factors of r squared and r squared sine squared theta. Okay. Everybody good? How many of you have seen something kind of like this somewhere? Okay, good. Now, what we're going to do, so I've given you the metric. Now what we're going to do is we're going to say, okay, we know what transformations we're allowed to do because we're allowed to do any transformation that satisfies that. Okay. I mean, earlier I wrote this as A transpose G, A equals G. Okay, our metric we're calling eta, and I'm just going to give a different name to the transformations because you are all aware the convention in relativity, special relativity, is to call these lambdas. If you're not, the convention in special relativity is to call these lambdas. So what we want to do is figure out from this, I love A so much, what are the lambdas? So we're going backwards now. We've got the metric of space-time and special relativity, and we would like to use that to find the transformations that we're allowed. Okay? And I have to say, this is pretty cool because this sentence could have been your answer to your first homework assignment. Like this, literally everything in special relativity follows from this. The constancy of the speed of light follows from this. Length contraction follows from this. Time dilation, the velocity addition formula, it all comes from this statement. Okay, and we'll tease some of that out in lecture, and then I'll let you do some of it in a homework assignment. But if you have the right tools in hand, you can actually state the premise of special relativity very concisely. Okay, so what we're going to do is look for these lambdas. Probably regret this, but so eta is diagonal minus 1, 1, 1, 1. That's just shorthand for it's a 4x4 matrix that's diagonal with those elements. Okay, so all right, so how many transformations am I expecting to have in special relativity? A lot. How many? An infinite number, right? But that's not feasible to write down. So we want to do something like what we did last time. We want to kind of get like some essential transformations. You know, kind of the ones that are independent in a sense. And you can make this more formal in other treatments. So, like for the case of rotations, where we said rotations in X, rotations in Y, rotations in Z. Okay? So first lesson is if you take Rx, Ry, and Rz, and you know, if you look at this for a minute, you're like, hey, there's the good old delta x squared plus delta y squared plus delta z squared. We know them. So we kind of expect this stuff to still be part of the story. All we're really doing is adding this. So maybe, just maybe, we have to add in this. Oh, well, you think that's going to cut it?
No.
Well, let me ask you a question. I mean, rotating around the x-axis makes sense, and rotating around the y-axis makes sense, and similar for z. Like, would it make sense to just rotate around t? Why not? So Madison is going to help us. We're in 4 dimensions. What's wrong with this? What is wrong with talking about a rotation around x when you're in 4 dimensions?
You're not talking about rotating around axes. You should be talking about rotating from planes.
Damn, you're good.
He
Yes.
whispered it in my ear, but I was thinking.
Okay, the problem is, and many of you have heard this from me before, but if you haven't, this is horrible notation. You should have never been taught a notation like this. This is absolutely despicable. Okay? This should be referred to as a rotation in the YZ plane, the ZX plane, and the XY plane. Because if you think about it, the only way you ever related these two things is because in 3 dimensions, there is a one-to-one isomorphism between a plane and the normal vector. If I say the xy plane, that immediately means the z-axis is perpendicular. But if you're in 4 dimensions, and I say the xy plane, there are 2 dimensions perpendicular to it. So if I say rotate around the z-axis, that's not really giving you a plane. So when we're talking about rotations, we really need to be talking about rotating in a plane and specifying the 2 coordinates that we're talking about. I mean, you just think about it this way. If you were in 2 dimensions, rotation still makes sense, but there's certainly no axis around which you're rotating. It doesn't exist. Okay? So in that sense, the natural continuation of this is as such. So we should really expect something like 6 things. These, of course, are just good old rotations. They don't do anything to time. They're just messing around with x, y, and z, but in the way that we're used to, because they appear in this combination that we've already dealt with. And then, Kara or Kara? Kara? Kara, what do you think we're going to call those other weird rotations? You want to phone a friend? That's perfectly legal.
Boosts?
Boosts, exactly. These are going to be the boosts. And I'm going to illustrate the connection between those and the things you're used to thinking about when you've seen, like, this frame is moving with respect to this frame and it's boosted and all that. We're going to get to that. Okay? All right. If you're curious about, so you might notice, like, there's this really weird degeneracy in 3 dimensions, right? You have, in 3 dimensions, you have 3 rotations because you have 3 independent planes. If you go to 4 dimensions, you get 6 rotations because you have 6 independent planes. Does anybody see the pattern? What?
Factorial divided by 2?
Close. It's actually dimension choose 2.
Oh.
So if you're not familiar with that, it's d factorial over d minus 2 factorial times 2 factorial. So in any number of dimensions, you can figure out the number of independent planes using that little trick. Okay? And, all right. Okay, so let's start with the case that we already know, and that is an example here. So if I'm, just to demonstrate that this works for rotations as well, actually I'm going to pick this example, so my little thing is going to go like this. So I want to write down an element of lambda xy, or I want to write down an element that corresponds to a rotation in the xy plane, but that thing has to act on 4 component vectors. Remember, everything we're dealing with lives in 4 dimensions. It's got a time component, an x component, a y component, a z component. And so I'm just going to write it down, and if you stare at it long enough, hopefully you can convince yourself that that is in fact what you would have expected. Okay. So let's just think about this for a moment. Of course, the top thing is going to rotate the c. I'm going to just write dt's and dx's because we're going to talk about differentials. So I don't want to do anything to time because I'm just rotating in the xy plane. And I don't want to do anything to z because, again, I'm rotating in the xy plane. And so the only thing that this is really going to mess with are these two, dx and dy, and it's just a 2 by 2 rotation matrix. Okay? And then you might or might not be aware that if you instead want to rotate in, say, the YZ plane, then this looks very similar. It's just you're going to use this lower 2 by 2 here. And if you do the XZ plane, then you got to do this guy, this guy, this guy, and this guy. Okay, but you have probably seen rotations in 3 dimensions. What I want to argue to you now, though, is that this matrix satisfies our defining condition that. Okay? And I am not going to write down lambda transpose and then write down eta and write down this. That'll take too long. I'm just going to write down what you get if you cram literally this thing into here, cram the metric into here, and then this thing into here. And what you end up is an expression that looks like this. Okay? So literally just plugging these things in and multiplying this matrix multiplication, you can all do that. Okay? And then what, of course, do you notice? What is that term? Is that term? That term? 0. Okay. So we do, in fact, get back the metric. Okay? Now you might be like, wow, Thornway is crawling. I knew how rotations work. Okay? Well, here's the thing. I know you know how rotations work, but this is worth looking at once, because now we're going to try and figure out these. And these are not as easy. The reason why the rotations look like this is because in this case, right, you're trying to work with this combination. I mean, you're also got dt and you've got dz, but we're not touching dt and dz. We're just touching x and y. So the fact that these are squared and added kind of screams at you, hey, make use of this. Right? And then, of course, that's part of the rotation story. Right? If we're going to handle these, we're now going to have to face something like this, where there's a minus. This is not going to cut it. Okay? So looking at an expression like this, which is what we expect here, because again, our metric is giving us a minus sign in front of one of the terms. Looking at this, kind of thinking about the inspiration here, what kinds of functions do you think we're going to make use of?
Hyperbolic.
Yes, hyperbolic. So we have that sinh squared plus cos squared of the same angle is equal to 1. Okay? So what we can immediately do is actually write down the form of a boost in, say, the tx plane, or the xt plane, it doesn't really matter. A boost in the xt plane we can write as cos phi, and now it's going to get a little bit weird, minus sinh phi, cos phi, and then 1's everywhere else. And a bunch of zeros. Okay? Now, obviously this works with hyperbolics instead of ordinary trigonometric functions, so that's one weirdness. But again, the motivation is that we know we're gonna have to generate a minus sign somewhere. The other thing is that this is symmetric instead of anti-symmetric like the one I erased, which you wrote on your paper. Okay, so you literally have the same signs across the diagonal, okay? Now, I'm not going to do it for you explicitly because you can do matrix multiplication, but you can take this transformation matrix and you can show that it satisfies this expression. Okay, it's just matrix multiplication. But what I want to do for you in the last few minutes is to take this thing, which is sort of naturally motivated by analogy to what we did here, okay, and just this observation that there's a minus here where here there were all pluses, and I want to connect this to what you've seen before, because this doesn't look anything like what you've seen before in terms of special relativity, right? So let's just make that connection, okay? And then we'll finish up here. Oh, all right. So let me see if I can fit this up here. So what I want you to think about is a frame of reference S. And then we're going to think about a second frame of reference, S prime, which is moving along the x direction with respect to S at some speed v to the right. So the velocity is in the positive x direction, okay? Because you know from the little bit of special relativity that you've seen wherever you saw it, that boosts, these rotations I'm saying are rotations in the xt and below planes, boosts are really these things. It's taking one observer and then moving to another observer's reference frame, which is in some constant velocity motion with respect to the original observer. That's what a boost is. It's different states of motion connected by constant velocities, constant relative velocities. Okay, so let's actually take the matrix and let's first of all see what it says about the coordinate transformation explicitly. So I can just get away with a little 2x2 version of this. So if I do c delta t, delta x, and I transform it by that, I'm going to have my cosh, and I'll just have an understood phi everywhere. So cosh phi c delta t minus sinh phi delta x minus sinh phi c delta t plus cosh phi delta x. That's my new vector. That's just matrix multiplication. Again, I'm just working with the 2x2 to make things easy. Okay, so here's the important observation, and this is one of those points where I'm going to do something, and you might be like, I never would have figured that out, and that's okay. I couldn't figure this out either. It's just the way that you derive it. You know, people took many years to figure this stuff out. So what we're going to do is we're going to use the following observation. And S prime, so to an observer in this frame, in S prime, the observer looking at the origin, so we're going to consider the origin of this reference frame. In S prime, this observer sees the origin at rest. That's what it means to be in a reference frame. Like you see the origin of your coordinates at rest. You move with the coordinates. Okay? So in S prime, we can say we can turn that into a mathematical statement. So delta x prime equals 0. Okay? But we have a formula for delta x prime. Delta x prime the new coordinates I get from the old coordinates by this transformation, so I can read off delta x prime as the lower component of that guy. So this tells me that minus sinh phi c delta t plus cosh phi delta x is equal to 0. Okay? But in frame S, the same origin, that's this origin, okay? I'm not talking about the origin in S. I'm always looking at this one point, okay? The same origin is moving at V. Okay. Now, if S was going to describe this thing moving, it would use the coordinates for S. So in S, you would say delta x over delta t is equal to V. Okay? Are you buying everything I'm saying? Good. Because we're going to take this and we're going to combine it with this. Because if you notice, both of those involve delta x's and delta t's. And so from that, combining these two, we can conclude that delta x over delta t is c times the hyperbolic tangent of that angle phi. Okay? Which again, we could just call v, the relative velocity of the two frames. Now again, like, don't be paranoid if you're like, I wouldn't have figured this out. I wouldn't have figured this out. Like, it's just, you know, just takes a while. You can get there. You can get there. It's got to happen, you know. But here's what we can do now. This is a nice way to get rid of this thing and replace it in terms of v. Okay, because we can immediately, of course, say that tangent, the hyperbolic tangent of phi is v over c. But better still, once you have this, you can go in and you can solve for cosh phi. And this just uses a little bit of hyperbolic trigonometry. Okay, cosh phi ends up being 1 over the square root of 1 minus v squared over c squared. And sinh phi, I'm going to define this thing to be what you probably know is called gamma. Sinh phi ends up becoming gamma times v over c. Okay? So then this guy, of course, is now going to be gamma minus gamma v over c minus gamma v over c gamma. And if you apply this thing to c delta t delta x, what you will find is exactly what you've seen in your special relativity class for the Lorentz transformation corresponding to a boost between two frames. All right? Now, I have in my notes like a little very, very quick, it's at the end of the last page of notes I'm going to post today. From this point, I mean, this is it. This is the connection to what you have seen before or will see soon. But I have like a 3-line derivation of the velocity addition rule, which at the beginning of this class I told you, like, that's one of the most trademark results of special relativity. So you can see where the velocity addition rule comes from. I'm not going to go through it right now. You would all follow it, so you could just look at it. What I'd rather spend the last few minutes doing is saying something that I don't have written. What this illustrates, I hope, is that when you first studied special relativity and you saw this stuff, it didn't make any sense. It didn't seem motivated. Like, why that weird factor? Somebody might have waved their hands and said some shit, I don't know. But to me, the idea that you can derive all of this stuff from something that looks almost exactly like rotations. Yes, there's a minus sign that makes you use hyperbolic functions, but otherwise the story is exactly the same. That to me is what I really like about doing special relativity this way, because rotations and boosts are really nothing but rotations in planes in four-dimensional space-time. This whole story comes from trying to think about special relativity in the language that you're familiar with, in terms of three-dimensional velocities, in terms of three-dimensional distances. In fact, when you study special relativity, you learn this really crazy thing that the length of something changes when you see it moving. You know, what did we talk about when we were talking about vectors in 3D with rotations? I said the length of something doesn't change. And then you get to special relativity and you're like, shit, the length is changing. And the time interval is changing. That only seems weird and hard because you're thinking about the length of something in 3 dimensions, you're thinking about a time interval, and you're thinking about that in a context where you should be thinking in 4 dimensions. In 4 dimensions, the lengths that you should be thinking about are the lengths between space-time points. That's a point with x, y, z, t, and another point with x, y, z, t. The length between those two things never changes. Okay? So special relativity becomes incredibly elegant and to me much simpler to wrap your head around if you do it in the appropriate number of dimensions, which is 4. Okay? That's where we're going to live for the entirety of this semester. But hopefully we've made some connections to things you've seen before. I am going to get to add in those extra 2 homework questions. Okay? So you're going to have another 2 questions in your homework assignment. So I will probably hold office hours Monday night as a consequence of that. Avery, you got a question? Okay, any questions? Yes?
Oh, so homework will still be due next Tuesday?
Yeah, homework will be due next Tuesday. Please get started on it as soon as possible, but I'll be here Monday night.
I'm sorry.
Sarah, you gotta stop.